I'd like to thank Dr. Janda, and it's really an honor to be able to talk to you today about some of the work that's going on in the Department of Earth System Science. I'm going to today give you an overview at the broadest level about what we can anticipate to happen over the next century in response to anthropogenic imposed greenhouse gases in the climate system. I'm going to then talk a little bit about some of my work on fires and interactions between the climate system and fires. And finally, at the end of the talk, return back to Southern California, to our backyard, to try to understand how climate's likely to change in the future and what the implications may be for future fire regimes. So to begin, I'd like to begin with showing you a picture of the time series of atmospheric carbon dioxide increase from the Mauna Loa Observatory from the work of Professor Dave Keeling and now his son Ralph Keeling. Dave was a professor at Scripps Institution of Oceanography and Ralph is a professor as well there. And they've continued this record. Paradoxically, they were able to go to this remote place in the Pacific Ocean on a volcano to measure carbon dioxide concentrations with an extremely high precision. And the measurements before they started in the late 1950s, were made primarily in urban areas, and they were incredibly variable. So there was really no picture of how the global background atmosphere was changing. And so we can see this relentless increase in atmospheric carbon dioxide. The scale here, this is concentration. It's proportional to the number of moles or the total amount of carbon dioxide in the atmosphere. And you can see there's a breathing of the biosphere, where in the summer in the northern hemisphere, plants take up carbon dioxide and they release it through the process of respiration, through decay, what goes on in the mulch pile during the fall, winter, and spring. So that leads to an annual cycle, and that's the natural carbon cycle, but we're perturbing it in a tremendous way, and there's a concave upward shape that's driven primarily by fossil fuel emissions. And so this is data on fossil fuel emissions that's compiled from taxation and records of shipping and coal, oil, and gas production. And I think there are a couple of important messages for this. This is what's actually driving the carbon dioxide concentrations. And what you can see here is that the total amount of carbon dioxide production from the top 4 producers overall is increasing through time. It's driven a lot by rapid increases in China over the last 4 or 5 years. There's been a tremendous increase where China has now surpassed the EU, 27 countries, and the United States. India is increasing as well. I'd like to draw your attention to the European curve here, where through investment in renewable energy, led by Germany and other countries, there's actually been a decline in the amount of carbon. And if you look at the United States, you can see the effect of the recession, but you also see a decrease in the last couple of years in the U.S. And what this is driven by is by natural gas, by fracking, by natural gas provides energy, and it provides it at a rate that produces less carbon dioxide. And so I think one message I'd like to leave you with from this plot is that in terms of slowing the buildup of greenhouse gases that cause climate change, there's hope. If we can build upon the natural gas conversion that's going on and strengthen our commitment to renewables, there's also a danger that the natural gas explosion, so to speak, will actually cause energy prices to remain low, and it'll be more difficult to have competitive energy from renewable sources. Another really important point in this context is that you don't need every country in the United Nations to reach a climate agreement. If you have 4 partners you bring to the table, you bring to the table India, the European Union, the US, and China, that accounts for 67%, the total is about somewhere on the order of 62% of global emissions. So that it is possible to imagine an international treaty with just a few countries participating. So a lot of that carbon dioxide is emitted by fossil fuels and also by land use change. Deforestation is another important source. So today we're emitting about 8.3 petagrams of carbon into the atmosphere. And in addition, from forest clearing in the tropics, there's an additional 1 petagram of carbon is going in, and some of it is accumulating in the atmosphere, and that's what's driving the concave upward curve, the monoloban curve increasing. But some of it's being soaked up by the ocean and by terrestrial ecosystems. And I think one of the things that's really exciting about UC Irvine is we have a number of colleagues who are working on all these different systems. And for example, Francois Pernot and others, Keith Moore, are looking at what's going to control the fate of carbon dioxide in the oceans. And is the ability of the ocean to continue to take up carbon dioxide and limit its accumulation in the atmosphere, how will that continue over the next couple of decades? And similarly, Claudia Zimze-Green is here in the audience, and Professor Michael Wielden and others are looking at how the terrestrial biosphere will change, and will it continue to be able to act as a carbon sink as drought intensifies, as permafrost changes and melts. So natural sinks in the ocean and in land are actually offsetting some of the accumulation of carbon dioxide that's emitted from fossil fuels. So to try to project the future, scientists develop scenarios of change. Some of the scenarios, what I've shown here, are the observed fossil fuel emissions into the atmosphere mostly from transportation, oil, gas. And what's shown here are potential future scenarios. And what's shown in the red is a business as usual scenario, which may be the growth of our total consumption of energy and fossil fuels if we do nothing to really mitigate climate change. In contrast, an RCP, these are different scenarios used by the Intergovernmental Panel on Climate Change. And here's another scenario that I'd like to draw your attention to, where we take steps to limit the amount of fossil fuel. There are systems that we convert our systems to renewable energy. Fossil fuel emissions peaks after a couple decades and then they decline. And I'm going to show you some of what the future may look like if we stay in a business as usual trajectory and we don't take steps to limit climate change. And this scenario, as you can see in the back, the gray lines are other sciences that are developed by scientists in past synthesis work. And the current Intergovernmental Panel on Climate Change is really focusing on these four scenarios. This bottom one is an incredibly aggressive scenario where you actually have to pull carbon dioxide out of the atmosphere in the latter part of the 21st century. And I'd like to point out that this scenario that I'm going to show you, this red line, it's actually conservative. This scenario was developed in 2005, and since that time, our emissions of fossil fuels globally have actually exceeded this scenario as it was developed by a set of scientists. So to study how these future emissions are going to influence the climate system, a number of us in the Earth System Science Department work with the Community Earth System model. This is a global climate model. It includes winds, ocean currents, heat transport, ozone. It has energy exchange on land. And recently, through work of many of us in the department, it has a carbon cycle, where carbon dioxide emitted from smokestacks goes into the atmosphere, it mixes through the atmosphere, it's taken up by plants, it's respired, fires will consume it and release it back in the atmosphere, it will be taken up by the oceans. And the way these models work, they're actually they're complex computer codes with millions of lines of code in them, and they resolve the world with a series of grid cells that are interacting. And so energy and momentum and mass are conserved within each of these little grid cells. So there's a vertical resolution and a horizontal resolution. So this is what it would look like over Southern California, at roughly the resolution of this model that was used for the simulations I'm going to show you at about 1 degree. So this is now work that was led by the Biogeochemistry Working Group within the Community Earth System model. And what I'd like to show you are some scenarios for that business as usual RCP 8.5 scenarios. The blue line is, again, with no steps to really limit climate change. This is what the emissions would look like over the next century. The middle panel shows the accumulation of carbon dioxide in this interactive carbon dioxide model, where the carbon dioxide is freely moving between the oceans, the land, and the terrestrial biosphere. And so if we do nothing, the carbon dioxide concentrations may increase to almost 1,200 parts per million. And this has implications for ocean acidification. This will acidify coral reefs. And if we do take steps, we can cut that roughly in half if we take steps to limit our emission of fossil fuels. And then finally, I've taken the privilege or I've converted most scientists. We work in units of Celsius, but I feel that Fahrenheit is much more visceral to myself and probably to many of you. I've converted what the temperature trajectory would look like for global temperature change. So we're starting out here. This is the baseline temperature for the planet, and then with the injection of the greenhouse gases and other ways that we're changing the atmosphere, we get an increase in temperature of about 2 degrees by today, and that matches the observations. And then we're expecting on the order of another 6 to 8 degrees of warming over this first century of continued use of fossil fuels. This is work. Some of this work. This is a figure modified by a postdoc, Gretchen Keppel-Alex, who works at UC Irvine. But I guess I think it's difficult when you look at a picture like this and you're thinking about what does it mean, the global mean air temperature? And I think there are a couple of things to think about when you're trying to relate it to the amount of change that ecosystems are going to go through. And I'd like to show you, this is a plot now showing the spatial pattern of that warming at the end of the century. So this is looking at the increase in temperature during the 2090s relative to what happened in the 1990s. And this is in degrees of Fahrenheit. And so you can see that over the oceans, you get the lowest amount of warming. Over land, you double it. There's less heat capacity on land. The oceans are really effective at absorbing heat. And as you move to the poles, you get even additional warming because you have feedbacks that kick in. You start to melt snow and sea ice, and that contributes to actually a darkening of the surface, and that leads to additional energy absorption, and you get additional warming on the order of in excess of 12 degrees of Fahrenheit of warming. So if we, now for my research, really one of the themes in my lab is really focused on interactions between climate change and climate and fires. And so we're really studying how the climate system is potentially influencing fire regimes, and that happens through rainfall, through changing winds, temperature, humidity, the length of the fire season, ecosystem composition, and human behavior. And so there are many ways that climate influences fires in different parts of the world. And a number of students here, including Xiaowen Lin, is studying, for example, how different management behaviors influence the way that climate influences fires in the United States. And also Dragana Motiva is studying how aerosols influence the climate system and human health through careful measurements of their isotopic composition. And Brendan Rogers is studying albedo and combining the aerosol and albedo and evapotranspiration effects in a climate model to estimate these interactions or feedbacks. So in our work, we use a lot of data from satellites. And there are a number of satellites that NASA has in orbit that are incredibly powerful for studying fires. And this is just an example of several. This is the NASA's Terra and Aqua satellites. They look like basically it's like the size of a school bus in space, and it actually takes pictures of the surface every 1 to 2 days globally. And it gives us really important information about fire emitted heat, surface reflectance and burned area, vegetation type and amount, surface temperature, carbon monoxide, which is a pollutant, and the smoke levels. And other satellites that are important include Landsat. It's really, I find it kind of interesting how all the satellites have different solar arrays that are put in different places. Some of them look really asymmetric and lopsided. And the Landsat provides burn severity, gives us information on deforestation, high resolution. Calypso is a satellite that sends a laser down and it gives us information about aerosols. And then what Dr. Janda mentioned, that Jake Miglietti has really pioneered in our department. This gray satellite measures the gravity anomalies around the Earth, and it gives us information about soil moisture, snowpack, and can be used for fire forecasting. So I've had the privilege of working with a team to try to measure fires around the world with colleagues from NASA and Columbia University, Duke, and University of Maryland. And we've constructed time series of global patterns of fires over the last 15 years or so. This is just a picture of the global pattern of fires across the world. You see fires in the Arctic, deforestation. I'll talk about that in a moment. Africa truly is the burning continent. There's a lot of fires in northern Australia, where my mom is from. And then also you have fires across Indonesia driven by deforestation and drought and burning of peatlands, and then many fires across the board. And we're really now at an exciting stage where we can actually look at long-term trends in different regions and try to understand how human controls and climate is affecting global fire regimes. So there are interesting stories in each region. I might draw your attention to a few of these areas where, like in Indonesia and Borneo and Sumatra, you have very strong El Nino control of fire. So there are big El Ninos in 97, 98, 2002, 4, 6, and 9. Southeast Asia, there's a large long-term increase driven by population increases and forest degradation. At a global scale, there's maybe been a slight decrease. Climate changes don't necessarily have to lead to more fires. If you run out of fuels, if the system dries out on a grassland system, you can actually have less fuel and less fire. And an example that may be contributing there is Northern Africa has a declining fire rate, and Southern Africa has an increasing fire rate. So we're trying to study each of these regions and trying to understand what's going on to better understand how fires are likely to change in the future. Just as a really brief example, we're also trying to study how fires in turn influence the climate system, and one way that they do that is through smoke. And this is an example from work led by Mike Koska, a graduate student in Earth System Science. This is smoke in the community Earth system model. So in that large climate model that I showed you, we've tried to isolate the effect of fires. And so we get a lot of smoke across the tropics from fires, and when we look at its effect on the climate, we find that it leads to a decrease in rainfall. Smoke aerosols tend to absorb radiation in the mid-atmosphere, and they tend to reduce radiation at the surface. And that, by changing the distribution of sunlight, you actually can reduce rainfall across many important tropical forest areas in the tropics. So that decrease in rainfall is shown here with the brown colors. And you can see that when you add fires into the climate model, you get a decline across the Congo, across the western part of the Amazon, and there are teleconnections that lead to decreases across the Pacific Ocean as well. The smoke aerosols have an important effect on human health. We've learned in the last year that about a third of the people that die from urban air pollution die as well from exposure to smoke from fires. But the distribution globally is fundamentally different. You have a lot of mortality from inhalation of smoke particles in the tropics, across Africa, and also in Southeast Asia, whereas the urban air pollution problem is really one that's in developed and developing countries. And this is worth using our estimates of global burned area and emissions and putting it through an atmospheric model. So this is it's basically the map up here shows you the level of smoke, how much smoke is present at the surface, and the impact on human mortality takes into account then how many people are present. So you see a lot of smoke in South America near the frontier of the forest, but there's not a lot of people living there, so you don't have as much mortality. But in Southeast Asia, where you've had large population increases, lots of fires, there's considerable mortality. So I'd like to turn and just spend a few moments talking about fire forecasts with a new project supported by the Gordon and Betty Moore Foundation. We're developing fire forecasts for the Amazon. The Amazon's a really important system in terms of biodiversity, and also in terms of the Earth system. It modifies the global climate system through the evaporation rates and through its potentially it can influence the climate system through its carbon stocks. And so what's shown here is this is the intact forest in the Amazon, and what you see in red is areas where you've had forest clearing over the last decade. And unfortunately, whenever there's a clearing, it's basically an ignition point for fires. So fires are used extensively on farms and ranches to maintain open areas for cattle or to clear crops. And in a dry year, an ignition point for a fire from one of these ranches will burn to the edge of the ranch, but then it'll keep burning into the forest. And it can cause damage, and it can kill the trees that are nearby. And so we've developed using information from El Nino. This is a map of El Nino here. And so we know that, for example, in Southern California, we have El Ninos. We have a really strong, more storms and higher rainfall during the winter. This is an El Nino event here in '97. And also we had weaker ones in 2002, 4, and 6, and 9. And then we've also found that the fires in the Amazon you can develop a predictive model several months in advance using information from the North Atlantic. So in the North Atlantic, temperatures of the ocean are warm, you generate more hurricanes, and counterintuitively, you also generate drought in the southern Amazon. And so this is an index of the temperatures in the North Atlantic. And in the last couple of years, over the last decade, it's been anomalously warm in the North Atlantic. So we've developed a forecast and a forecasting model. And on the left-hand side is the predictions, are the data. So these are low fire years here, and these are high fire years on this side. So 2005, 7, and 10 were big drought and fire years in the Amazon. And many hundreds of thousands of kilometers of forest burned. And our predictive model with lead times of 3 months that will enable use and conservation are able to predict the actual observed pattern from the satellite in each of these years. And we actually built the model using data up to 2009, and our 2010 forecast was a true forecast. And we're now really working on developing forecasts year by year, and so we've made a forecast for 2013. This is our forecast for 2012. We predicted a below fire year, so here's 2012. So the fire season in the Amazon, across the southern Amazon, is in August, and we made this forecast in April. And so you can see what our forecast was, and then the dot is how well our model did for this last year. So we have a ways to go for some regions. We are off, including in Peru, where there may be an upward trend in fires. But for many other regions, we're able to actually predict reasonably well and provide information then that's maybe useful for conservation efforts to limit these fires. And we think that the key mechanism that allows these forecasts, there is a physical basis, and it's based on trees. That if the trees in the Amazon and the soils aren't recharged fully by moisture in the preceding wet season, then they won't have enough moisture to evaporate and humidify the atmosphere during the following dry season. So now to conclude my talk, I'd like to turn to our home, our backyard to Southern California. And this is work led by Yufang Jin, and he's a project scientist, he's a researcher in the Department of Earth System Science. And these are pictures of fires that have had a massive impact on our economic systems in Southern California. This is the Santiago Canyon fire shown here, I believe, that happened in 2007. And then this is the station fire that burned above JPL in 2009. And what Dr. Yufang Jin has been able to do is to separate the long-term time series of fires that we have in Southern California and separate them in the ones that are associated with Santa Ana winds that are blowing offshore, and then ones that are not. And these are typically summer fires. And so you can see here that during Santa Ana, you have all the smoke that's blowing out offshore. And you have really high winds, and that's what makes these fires particularly devastating. You can contrast that with the station fire. See the direction of the smoke plume? It's going up to the north. So it's being carried in a different direction. So Dr. Jin's been able to actually develop predictive models of how these fires are varying from one year to the next, and they depend on climate. So in the fall, in years where you have higher temperatures and lower humidity during the summer, you tend to have more summer fires. And in years where you have lower precipitation in the fall, you tend to have more of these Santa Ana fires. So these are the trends by decade now. So what's shown here is the number of fires. This is the burned area, the amount of area that's affected by fire, and this is the fire size. And burned area is kind of a nice proxy for the impact on ecosystems and on economic systems. And you see that there's this, for the summer fires, they're shown in green. There's actually been a marked increase over the last several decades. And for Santa Ana fires, it's more noisy, but we certainly had a lot in the last decade, both with 2003 and 2007 having large events. And this trend in burn area is being driven primarily by the number of fires has actually remained relatively constant or declined a little bit, but each fire is burning to a larger size, and that's what's shown here. And that's partially under a climate control. So if we now look tunneling in with that business as usual scenario, but looking at the middle part of the century, this is what the amount of warming that we expect to see in Southern California. So here's San Diego here, Irvine, I think you may be able to see if there's an outline of it here. And this is a additional amount of warming that we expect above what the climate was from 1985 to 1999. So this is going from 1.5 to 4 degrees Fahrenheit. So that's how much higher on average the temperature will be in the middle of the century, like 2045 to 2060, with climate warming if we don't take steps to limit our emissions. And what you see is there's a strong gradient because of the heat capacity of the ocean. Because if you live on Balboa Island, you're in luck that there's going to be less climate warming. However, you will be impacted from sea level changes. But as you move into the mountain systems, where a lot of these fires are occurring in the mountains behind San Diego, Santa Ana, and up in the San Gabriels, you get much more rapid warming. There's the effect of the greenhouse. There's less heat capacity on land, and there's less water vapor to mask the effect of the carbon dioxide. And the warming is actually greatest in summer. So if you remember the heat waves that we had this last September, imagine them again with an extra 5 degrees. You know, what kind of an impact will that have? And then you also get warming during the fall. So this is the trajectory in the middle of the century of temperature. This is what it will look like at 2045 in the red compared to what it is today. And then this is what the rainfall might look like. The contemporary is in the blue, and the red is what it might look in the future. And there may be a little bit less rainfall during the fall from this community Earth system model prediction that's been downscaled using a regional model, using work from colleagues at UCLA led by Alex Hall and Scott Cass. And so Dr. Jin has made a prediction for summer fires based on her regression models with climate. And she predicts that these summer fires are going to become more frequent. We'll have both, the number of summer fires is likely to increase, so the purple is what we expect in the middle of the century versus the blue, the contemporary level, and then the fire size is likely to increase as well. So we haven't yet actually worked through exactly, and we're in the middle of this large NASA project to try to understand what's going to happen with fires during the Santa Ana times. And we've also just started a project with support from the Jenkins family to actually study more broadly how is the vegetation going to change in the middle and latter part of the century in Southern California in response to fires, but in response to other factors like can the plants survive in midsummer in response to drought if we have additional warming during the summer. And what I didn't show you is that the humidity also drops a little bit. So in conclusion, climate change impacts are likely to be considerable. This is a picture of the Santiago fire burning at night here in Irvine. Will be considerable if no concerted action is taken to limit emissions. So we need steps at all levels, from the local to the international, to limit emissions to avoid the consequences of considerable climate change. The spatial and temporal pattern of fires will change with warming, with important consequences for ecosystems, human health, and climate. In my opinion, I feel that we're going to need to actually actively manage fires much more than we have in the past. There has been an ethos in parts of the West and in Alaska where the large wildfires are allowed to burn because they're not going to damage systems. But taken as a whole, if we want to see the ecosystems look the way they do today and limit the carbon losses, I think we're going to need to take steps to actually suppress them more actively. And I think in the Amazon, we could develop better fire forecasts to do this and then use that information to redirect firefighters to potentially design incentives for ranches and farms not to burn during extreme drought years. And in the West, I think we may need to think about investing more heavily in suppression efforts, including like smoke jumpers that might jump on a fire just as it started to try to suppress it before it grows into a larger conflagration. And so we're in the process of actually extending, we're trying to, over the next 5 years, we're hoping to extend forecasts for fires to other parts of the world, and we think it's possible wherever there's a mechanism where, for example, the snowpack or soil moisture during the winter may influence then the amount of water that plants have to transpire and evaporate in summer that then influences the regional climate. So with that, I'd like to acknowledge my lab group and UCI collaborators, collaborators at other universities, including our colleagues at JPL and at UC UCLA and the funding support from the Lincoln family, NASA, the Gordon Betty Moore Foundation, and the National Science Foundation. So thank you.